We have a slightly more challenging Coulomb's law question. Let's say that we have two positive charges. Q1 is 4 nanocoulombs. Q2 is 9 nanocoulombs. They are separated by 5 centimeters. So the distance between Q1 and Q2, which I have labeled, I don't know if you can read it, it's labeled R12, just the distance between 1 and 2, is 5 centimeters. Okay, fair enough. But what I want to know, if I place a third charge in between these two, I'm going to place a third positive charge in between them, where would the net force on that third charge, what location? I'm going to measure it from charge 1. What location measured from charge 1, other than infinity, would the net force acting on that charge be 0? Of course, if something's infinitely far away, the force is reduced. They tend down to 0. They're basically 0. Other than infinity, where could you place a third charge and have the net force be equal to 0? It's a positive charge. If I place it, it's going to be somewhere over here, all right? That's a stronger charge. That's a weaker charge. It's going to be somewhere further away from the positive, because it's positive. These forces are repelling, these charges are repelling each other. I'm going to place a third charge, Q3, over here somewhere. So that's Q3. And I want to figure out that distance. I'm going to label it X. I don't even know the value of Q3. I don't need to know the value of Q3 because it's going to cancel out. Yay! Okay. Well, if you draw a force diagram for charge 3, it's going to look like this. I know that charge 1 is going to repel charge 3 to the right. So that's the force of charge 1 on charge 3, F13. And I know that charge 2, which is also positive, is going to repel charge 3 to the left. Right? It's pushing it away to the left. So that force would be that way, the force of 2 pushing on 3. Okay, F23. And I know these are going to be equal to each other in magnitude, opposite in direction, but equal in magnitude. How do I know that? Because I'm looking for that place where the net force on charge 3 is 0. That's the question. What's the value of X such that the net force acting on charge 3 is 0? Well, I'm just going to write the equation. Ignore any negative signs. They're going to equal. These two forces will be equal and opposite, so they're going to have the same magnitude. Let me write an equation for F23. So F23, F in magnitude. Let me write it this way: F23 will be equal to, in magnitude, to F13. Okay. Well, what's F23? It's going to be K times Q2 times Q3 all over. Well, what's the distance from, let's see, this is 2, 3, so that's that distance. Well, what is that distance? It's 5 minus x, all right? 5 minus x is that distance there. 5 minus x squared. Now you might say, Mr. Wyman forgot to convert that to meters. If I were calculating a force, I'd have to, because a Newton is based on a meter, not a centimeter. But I'm not calculating a force. I'm going to calculate a distance, and I'm just going to leave it in centimeters. Okay? If I were calculating, if you're not sure, convert. Better to be safe than sorry. So that would be 0.05 minus x. And then your answer for the value of x would be in meters. Anyhow, over here, F13, K, Q1, Q3, all over the distance between those two, which is x squared. Now, I love it when this happens. Look at all the stuff that you can cancel. For start, oopsies, bad teacher, that was a... Sorry. Okay, once more. This is the force between charge 2 and charge 3, which we know is to the left, because that's pushing charge 3 to the left. That one is repelling it. That is Coulomb's law. K Q2, Q3, divided by the distance from here to here squared. And that's so Q2, Q3. And then over here, F13, that's the force. This is pushing that to the right, right? That's repelling that to the right. The whole thing is focusing on this point. So that's repelling that to the right. K, Q1, Q3 over x squared. Anyhow, K and K are both on sides. Those cancel. Q3 and Q3 cancel. Now you can simplify this thing. And I'm going to go ahead and put some numbers in here. Q2 is 9 times 10 to the negative 9 divided by 5 minus x all squared. Q1 is 4 times 10 to the negative 9 divided by x squared. There's one other thing you can cancel simply because these are both nanocoulombs. You couldn't do this if they had micro and nano or something like that. But because they're both nano, the 10 to the negative 9s cancel in this case. Okay, so I'm just going to rearrange this. Then I'm going to show you something here. I'm going to divide the 4 to the other side over here. So divide both sides by 4, and I'm going to multiply both sides by 5 minus x squared to get that over to that side. So I'm going to end up with 9 divided by 4, and I divided that to the other side, equals 5 minus x squared all over x squared. Now, this is something that I don't know if it occurs to you or not, but instead of expanding this binomial, which you could, would be a pain in the derriere, instead just take the square root of everything. You can take the square root of the left-hand side and the right-hand side, which is always permissible. I'm going to move this over here. So we have, well, just write it like this, the square root of that and the square root of that. Well, I love it. You can see I chose these things intentionally. The square root of 9 is 3 and the square root of 4 is 2. So that's 3 over 2 equals, well, that squared is just 5 minus x, and that squared is just x. 5 minus x all over x. Now, let's multiply both sides by x, multiply both sides by 2. So I get 3x equals 2 times 5 minus x, or 3x equals 10 minus 2x. Now add that to the other side, so I get 5x equals 10, and x equals 2 centimeters. I like that problem. We're done. So that is 2 centimeters from Q1. It would be obviously 3 centimeters from Q2. Yay!